We just discussed before the 4 different classes of second order system, but we never discussed before what is the implication of these 4 different classes of the system. What is the implication of the zeta value, whether it is greater than 1, less than 1, or if it is 0, to the dynamic behavior. Or in particular, if we want to see what is the effect of this parameter zeta to the step response. This is what we are going to discuss now. What is the step response of a second order system for these different classes of system? Let's start it to look at the first class of a second order system behaves when we give a step input to the system. So let's take a look on the step response of an overdamped system when the zeta in our second order system is greater than 1. To analyze, let's take a generic case of a second order system, but to make our analysis simpler here, in a sense, let's just consider a case of a second order system when the DC gain K is equal to 1. If you have a generic second order system but DC gain is equal to 1, the transfer function of the system will be like this, right? We have discussed before, when we discussed about an overdamped system, that if you have overdamped system, you will have 2 real negative poles, right? 2 real different negative poles. You have S1 and S2. Both of them are real number, but S1 is not equal to S2, right? This is what we discussed before when we have an overdamped system. So the transfer function of our overdamped system can be rewritten like this, where S1 and S2, you know how to derive S1 and S2 before. In a S-plane, S1 and S2 will be located at 2 different locations on the real axis. The poles S1 and S2, the one that we derived in the previous few slides when we discussed about overdamped system, are like this. Both of them, again, if you look at it, both of them are real numbers. If you consider a stable system, so both of them will be negative real numbers. Now, let's evaluate the step response of this system. Instead of using this transfer function, now I will use the simplified transfer function after we factorize the denominator. So to evaluate the step response will be equal to the transfer function times the unit step input. This is the response, but remember again, this is still in Laplace domain. So when you want to convert it to time domain, you have to do a partial fraction expansion, and then again you refer to the Laplace table, you will get the response Ct in time domain like this. You can try it by yourself. Where S1 again is this, S2 is this, right? Both of them are real negative number. Once you get the response in time domain, we can try to plot it. So I will just take a arbitrary number for the omega n and zeta, as long as zeta is greater than 1, and then I just plot it here. So this is the response in time domain here. This is in particular an example when zeta equal to 2. 2 is greater than 1, right? So definitely this is an overdamped second order system. Using the expression of the step response in time domain that we derived in the previous slide, I can plot it with any arbitrary omega n value, and then I use zeta equal to 2, and then after I plot it, the response looks like this. So this is a typical response of an overdamped system. Now let's take a look when we have a critically damped system. Critically damped system is when your zeta is equal to 1. When your zeta is equal to 1, what you will have? You will have 2 identical real poles which both of them are located at the same real axis, right? When you are going to analyze the unit step response, how to do, you multiply again the transfer function. Now the transfer function looks like this, right? After you factorize the denominator of the transfer function, and then we multiply it by 1 over s, because 1 over s is the unit step input. And then after that you do partial fraction expansion. After that we refer to our Laplace table, and then we converted the response to a time domain. We have two identical real poles here. So the response in time domain looks like that. In S-plane, this is just to refresh again our memory on a critically damped system. In S-plane, we will have two identical poles located at the real axis. After you analyze the unit step response, you get this unit step response in time domain, and then you can plot it similarly like what we did in a overdamped case. So I use the same omega n just for illustration here, but in particular to illustrate the critically damped system response. So I use zeta equal to 1, and then when I plot it, the response looks like this. What do we see here? It seems that the response of critically damped system is somehow faster than the response of a damped system, right? What do I mean by faster? Of course, the critically damped system reached the steady state condition earlier than the overdamped one. So this is an illustration of a step response of an overdamped case and of a critically damped case. Now, let's take a look about underdamped system. What is the step response of an underdamped second order system? We discussed that before. For underdamped second order system, we will have two complex conjugate pair of poles, right? One is here, the other one is here. So our poles are complex conjugate pair. We are going to analyze the step response. So how to do that? Again, same thing. I multiply the transfer function with the step input in Laplace domain, which is 1 over s. I do partial fraction expansion. This is what I get after I did partial fraction expansion, and then I refer to the Laplace table to convert the response to the time domain, and this is the step response that I got in time domain. How do I come up with this sign formula on it? Because I have a complex poles in my system. If it's complex, then you will end up with a sign terms in your response. Okay, you can try it by yourself to convert it to time domain, but in short, your unit step response of an underdamped second order system will be like this. Now let's try to plot this response. Just for comparison, I still keep the step response of the overdamped and the critically damped system before. Now I will plot the step response of an underdamped case using the formula that we just derived in the previous slide. So this, the one in red now here, is the underdamped step response when in here in particular I take zeta equal to 0.2. So it's between 0 and 1. What do you see if you compare this to the overdamped and critically damped response? We see an oscillation on the response, right? So the response is oscillating. Somehow the response is faster. It reached the steady state condition much earlier than the overdamped and the critically damped case, but the response is oscillating before it is stabilized after some time. Okay, This is typical response of underdamped case when your zeta is between 0 and 1. Let's take a deeper look on the step response of an underdamped case. In this slide, you can see an arbitrary step response of an underdamped case. So the response is oscillating like this, even though after sometimes it is stabilized, right? But at the beginning, it is oscillating. In particular here, the oscillation of this kind of response of underdamped case, the amplitude of the oscillation is decaying. At the beginning, the oscillation is very large, but then it's getting smaller and smaller and smaller. And the decay happens in an exponential rate. So the decay of the amplitude happens in exponential rate. The sinusoidal that you see here, the oscillation that you see here is because of the imaginary part in your poles. So this is just one quick look on the typical step response of an underdamped second order system. The frequency of oscillation, so you see there is an oscillation here, right, in your response here. The frequency of oscillation is equal to omega d. So what do I mean by the frequency here? So it's the frequency in one wave, in one oscillation from peak to another peak. Okay, so the frequency is equal to omega d, where omega d is determined by the parameter of the second order system by omega n as well as the zeta. Few notes again on the step response of underdamped system here. The lower the damping value, the lower the zeta, the more oscillatory your response will be. The larger the zeta, the less the oscillation in the response will be. It's pretty intuitive, isn't it? When zeta is getting larger, then it will exceed the value of 1, right? Underdamped, remember again, underdamped case is when your zeta is between 0 and 1. So the larger the zeta, so underdamped case is between 0 and 1. So if this is 0, this is 1, this is when you have underdamped. This is when you have overdamped. The larger the zeta in your underdamped system, the less oscillatory in your response. That's pretty intuitive, because when it is getting larger, you will tend to enter the overdamped area. When you are in the overdamped case, you don't have oscillation in your response. So that's why the larger the damping, the larger the zeta, the less the oscillation in your response. What happens if the zeta is getting smaller? If zeta is getting smaller, of course, the oscillation is becoming more. Intuitively, when there is no zeta at all, or when zeta is equal to 0, the response will become oscillating all the time. Okay, it's always oscillating. There won't be any decay on the response. That is when zeta is equal to 0, or when we have undamped case. Zeta equal to 0 is undamped case, right? In the next slides, we will take a look what will happen if we have really zeta equal to 0, or when we have undamped case. So this is for a case of undamped second order system. You still remember we discussed this. When we have undamped case, we will have a imaginary conjugate pair of poles, which means that we have poles where these two poles are conjugate to each other, but the poles are located at the imaginary axis. Okay, so the poles are plus minus j omega n in this case. How to analyze it, you know how to do it. I will not go too detail on it, but then at the end you will get the response, and then when you plot the response, I'll plot it together with the previous three case, you will have the blue step response. If you look at it, the response is indeed oscillating all the time. The amplitude never decays, the blue one. So this is the blue one, is the case when the damping ratio zeta is equal to 0. It's always oscillating. The amplitude is not decaying, so it's not stabilized in the sense. So we have three illustration here when zeta is greater than 1. For simple illustration, I take zeta equal to 2. When we have critically damped system, when zeta is equal to 1. When we have undamped system, when zeta is equal to 0. And when we have underdamped system. For illustration here, I put when zeta is equal to 0.2. I explicitly mentioned in the previous slide, for the case of underdamped system, when zeta is getting bigger, closer to 1, the oscillation will be less. When zeta is getting smaller towards 0, then the oscillation will become more. So let's take a look here. I'll put more illustration here for different zeta. This is when zeta is equal to 0.1, the green one. If you look at this illustration, the oscillation is becoming more than the one from zeta equal to 0.2. When zeta is equal to 0.3, the oscillation is less. 0.4, 0.5, etc. It's becoming less, less, and less. Until when your zeta is equal to 1, there is no oscillation at all. So again, when you have underdamped case, there always be an oscillation. But the greater the zeta, the less the oscillation will be. To summarize what we just discussed about the response of different types of second order system. So you can see the summary on this table. When zeta is equal 0, which means we have undamped system, you will have imaginary poles, imaginary conjugate poles, and the step response. The step response is always oscillating. The amplitude never decays. When we have zeta between 0 and 1, this is when you have underdamped. In that case, you will have complex conjugate pair of poles at this two location probably. The step response of this kind of system is oscillating, but the amplitude is decaying until at the steady state condition, the response is becoming constant. Remember again here, we are only talking about stable system. And then when we have zeta equal to 1, this is when we have critically damped system. We will have two identical poles in the real axis. This is the first time we will get non-oscillating response from an underdamped case when we increase the damping ratio zeta. The last one is when we have zeta greater than 1. This is what we call as a overdamped case. You will have two different real poles. Considering a stable system, the two real poles are in the left-hand planes, of course, and the response will not oscillating as well like this. But the response will be slower than the critically damped. So these are the summary of step response of different types second order system.